Welcome to lecture 15. This is our intermission 1. We take a little time between the end of our coverage of mechanics and the rest of the semester to look over what we covered in units 1 and 2, and we look ahead to what's coming up in the second half of our semester. But first, since we have a little time in this lecture, we will go over some essay questions. These are the multimedia-oriented essay assignments that we used to have. While you haven't and won't, see this as your assignment. Some of the essay timed assessments are based on these, so you might want to make sure that you feel comfortable with them. In the mechanics overview section, we will review what we have covered so far, emphasizing some of the common themes that reoccur in multiple different contexts. Then, since we are at about halfway point in the semester, we will look at what you will see as we cover the laws of classical and modern physics in the next few weeks. Enjoy this week's half break. You earned it. And attempt the timed assessment when you feel ready. And remember, all the written works, including the timed assessments, are basically practice, a way for you to test yourself on how much you learned. Then, on to the essay questions. So, I was thinking about what to cover in this intermission video. I have something that I recorded last time I taught this class, just giving a bit of an overview of Unit 1 and 2 that we have covered so far, and have a kind of forward-looking thing about the classical and the modern physics that you will see coming up. And I was thinking about doing a kind of Units 1 and 2 overview with the mind maps, but I don't know if that'll add anything here. I mean, I do have the mind map here, but the overview of Units 1 and 2 that I already did kind of goes over the same thing. And while this is, more detailed, there are more branches, and computer doesn't forget, so it probably touches on the things that I left out in my previous 20 minutes or so of overview. But I don't know. I don't think longer necessarily is better. Like, for an overview, more comprehensive doesn't necessarily mean it's gonna be more useful. I think yeah, so I'm just expanding all these out so that people can at least see. And if you want to make a use of it, then you can go to this notebook LM site on your own and explore sources and this mind map stuff. Go to coaphys.xyg/ this is a short link 1010 and then LM. It can be capital LM or lowercase lm. I made enough aliases for the link that they will all work. So I don't think I'm gonna do an overview using this mind map because I don't think I'm adding anything there by doing that myself. And so I was thinking about what would be useful to people. I did do the timed assessment demo at the end of Unit 1, and the logistical details haven't really changed. And as far as the content goes, you have your homework assignment, the question set, and so I think the homework assignment, reviewing those, will be actually more useful to you. So I think doing another set of timed assessment demos will really help people that much. And thinking through it, I realized the one thing. So let me give this as an example. So let me go into my open math thing, and I will use one of the essay timed assessments for Unit 2 chapters. I think one of the useful ones gonna be, I can probably look at the essay timed assessment for chapter 5. I think that's the one covering oscillations and waves. And let me just show you some of the questions that are here. I already did the demo of question 1. This is the question that doesn't really change from chapter to chapter. It's basically the same open-ended question. I already did the demo for that. And for the second question, you can potentially get one of the three questions. And the way these were written, many of them, they were written with the understanding, assumption that you have seen something like this in the context of assignments that we don't have anymore. We used to have a multimedia oriented essay assignment where you watch some video and you answer some questions. And this Chladni figure was a topic in one of those. And even though I did record a short segment involving Chladni figure, I think there may be still some gap just because these essay assignments, we don't have them anymore. And some of the essay questions, essay timed assessment questions that you will see, they were written when we used to have those essay assignments. So by basically not having the essay assignment, even though I try to fill in that gap here and there, I might have forgotten to fill it. So I think covering that potential gap is going to be more useful for people than anything. And this is also an opportunity for me to kind of show the material that did used to cover like lecture like a thing, but we don't do that anymore, mainly because when I was putting together updated course material for this semester, not having taught this class since before AIs were a thing, I think these assignments are they are really susceptible to people just using AI. I worried about people just answering this with AI, and they were peer graded assignment, but then people might also peer grade with AI. It's like, what's the point? That was my main worry, so I just took them all out. When you got through unit 1, you didn't see chapter 1 and chapter 2 essay assignments. Hopefully the essay timed assessments are okay, not having seen this. And then we have more chapters now, chapters 3, 4, 5, 6, and chapter 7 fluids. It was always kind of light enough that we didn't have an essay assignment, and I don't think there are any essay timed assessments either. So all these, some of these cover lecture-like material that in the old videos weren't covered in the lecture because I was relying on people basically, doing the essay assignment. So let me go over this. I think going over this will be more useful than anything else. And let me actually go back to Unit 1 material since we didn't do this for Unit 1 review. So even though there isn't going to be a focus on chapters 1 and 2 as you do Unit 2 timed assessment to wrap up Mechanics 2, I think there's some value in going back to this. So essay assignment for chapter 1, kinematics, you can see that they are not published because I'm taking this out of circulation. We are not doing this anymore. So I guess so these are based on videos, but for copyright reasons, I don't think I can really play the full video here. At least definitely not with the audio on. I think what I'm gonna do is I will open it here and I'm gonna mute the sound and not play the whole thing with the sound on, but I will turn on the subtitles when they have it. When they don't, then they don't, and I'll just skip around in the video and just explain what they are supposed to illustrate. I guess I can read out loud the assignment instructions. So in this essay assignment, this is for chapter 1, kinematics. You will see an important principle of projectile motion demonstrated. Please watch the following physics demonstration video from Harvard Natural Sciences lecture demonstrations and answer some of the questions below. And if you want to watch the video, there's a kind of video ID here, and you can also search for shoot and drop video that's posted at Harvard Natural Sciences lecture demonstrations channel. You can go watch it yourself. So here I'm just gonna mute the audio, and now I'll just skip around for key portions of the demo. So this kind of the apparatus that Alan is setting up is to demonstrate two balls that's gonna be set in motion in two different ways. One, this yellow ball here is gonna be simply dropped, and I think it's the red ball on the other end is gonna be launched sideways. Oh, they are both yellow. So he will do that, and as you see that, what you are supposed to observe is that this ball that's simply being dropped and the ball that's being launched sideways, they hit the ground at the same time. So that's what you're supposed to see in the video. Now it says, for the essay assignment, consider following 4 questions and choose 2 to answer. So you know what I'm gonna do is, I guess I can just show you the model answer and just read it out loud. And if there's any more commentary that I think I should add, then I'll do that. So question 1. In one paragraph, explain what happens with the 2 balls, what happened with the demonstration that was interesting, what do you think is the physical principle being demonstrated through this example, why do you think the balls move in the way you saw and strike the ground in the way you saw. And let me open the model answers. Model answers are in this peer grading item. Again, these used to be peer graded assignments. I'm not doing it anymore because of AI. These were frankly not the most AI proof assignments, like, or even Wikipedia proof assignments. So question 1, I already read it. The summary of the question is, in one paragraph, explain what happens with the balls. And my model answer is, in the demonstration, you see 2 balls falling. However, the ball on the right is given an initial rightward horizontal velocity, while the ball on the left is dropped from rest. Despite this difference in the initial horizontal velocities, you see both balls hitting the ground at the same time, because both balls have the same vertical velocities from the start to the end, and experience the same vertical gravitational acceleration, and the motion in vertical and horizontal directions are independent. And this is the main principle being illustrated. The vertical and horizontal directions to perpendicular directions, the motion in those directions are independent. Okay, let's look at question 2. Consider the following statement. In this shoot and drop demo, the 2 balls have different velocities compared to the other ball throughout their motion, but they have, this is the statement. So let me continue reading. The different velocities compared to the other ball throughout their motion, but they have the same accelerations compared to the other ball throughout their motion. Is this a true statement? Justify your answer by pointing out particular features you noticed in the video and by using the physics definition of velocity and acceleration. I guess nothing stops you from looking at the model answer as I'm reading out loud the question. But I do want you to give it some thought before you look at the model answer. So this is the model answer. Evaluation of statement. I guess I won't read out the statement again. It's the exact code of the statement I read before. And this is a true statement, in particular to the second part, dealing with the accelerations. Since the 2 balls have the same accelerations, vertical, downward gravitational acceleration at about 9.8 meter per second squared. The first part requires a little qualification. The 2 balls have the same vertical velocity throughout their motion. They both start out not moving vertically. They have different horizontal velocity in their motion. The ball on the right start out with some, the ball on the left start out with none. One could correctly summarize this as having different velocities, but a pickier individual might clarify which component of velocities are the same, which are different, and on the basis of this distinction, evaluate the statement as not being completely correct. By the way, because this is essay assignment, there's always a kind of open-ended aspect to the questions. Model answers, again, they are a model. There could be many other versions of answers that are completely correct. That's not exactly the same as the model answer. Okay, let's look at question 3. And think question 3 is still about that video, the shoot and drop video, and for question 4 I'll have to play this video. So question 3. Imagine this experiment, let me hide this. Imagine this experiment was carried out so that the ball being shot out to the right was shot out twice as fast as seen in above video. Will both balls still strike the ground at the same time? Explain why or why not, and make sure to explain what changes and what doesn't change. And if you understood the whole thing about the vertical and horizontal directions motion being independent, then you might easily say, oh yeah, they should still strike the ground at the same time. Probably. Let's read my model answer for question 3 here. Will both balls still strike the ground at the same time if the ball on the right is shot out faster? Yes, because motion in horizontal and vertical directions are independent. That's the main key point. Additional horizontal velocity does not change the vertical motion of the ball that is being shot out, so it still strikes the ground at the same time as a ball being dropped. Initial vertical velocity is not changing, and this is important in ensuring both balls drop at the same time. So the one care they have to take in setting it up was that the ball being shot out horizontally is being shot out horizontally and not at some angle. If it's at some angle, then it'll ruin the demo. Okay, so for question 4, I need to watch or I need to show a different video. So let me show it here. And again, I can't quite show the whole video for copyright reasons. Let me just skip around the key portion of it. So this is where you see the setup. This is the gun. It's laser aligned to this target monkey. It's a tranquilizer dart that's gonna hit the monkey. And let's see, do I see the laser thing be named? Oh yeah. So as the laser thing is aimed at the monkey, you see that, so that's how the target is aligned in a straight line. And the projectile is fired, and in the monkey cam, I think we are gonna, see it get hit, and in the camera, so you see the two are launched and released at the same time, and the ball, which was aimed straight at the monkey, it drops just enough to hit the monkey as it's dropping down. So this is a classic demo. I don't think I do any version of this in the newly compiled lectures. So this is one of the reasons I'm doing what I'm doing now. So again, if you're interested in the full video, you can search Shoot the Monkey video at their channel and watch it yourself. So now the question. For this question, look at the following additional video demonstrating the classic Shoot the Monkey experiment. I kind of skimmed over it. To briefly explain what is going on, and here's the description. I guess I didn't actually have to watch the video. The launcher is aimed directly at the monkey by aligning the laser sight to the monkey. At the push of a single button, simultaneously the monkey is released. There's some sort of electromagnetic thing up there. The monkey is released and the ball is fired. And 3, even though the monkey drops from where he was when the launcher fired, he still manages, or not even though, maybe because, he still manages to get hit by the ball. Okay. So here are the questions I want you to address in your answer. Why was the monkey hit by the ball? And would the monkey have been hit if he continued to hold on, staying where he was? If the ball was fired at a faster speed or slightly slower speed, not change the angle of the aiming, will it now miss the monkey? And this is the model answer. Shoot the monkey demonstration. The monkey is hit by the ball because, in some sense, both the ball and the monkey fall under the gravity by the same amount in the time it takes for ball to travel to the monkey's location. For the monkey, I think it's easy to see. So in the case of the monkey, it is falling literally from its starting position. In the case of the ball, it is falling as compared to a straight line trajectory it would have moved in the absence of gravity. The remaining answers for the other series of questions there. 1, the monkey would not have been hit if we continue to hold on. You can kind of see it in the video. the ball falls, but the monkey does not. 2. As long as the ball was fired fast enough to hit the monkey before it hits the ground, it would hit the monkey whether it is fired at a faster or slower speed. Now, so for the faster, there's no limit. For the slower portion, if it's so slow that it wouldn't have reached the monkey before monkey hits the ground, then yeah, it'll probably miss the monkey with all the bouncing and all that. So that's this essay assignment. Now, I'll have to watch the time for the remainder. It's possible that I'll have to edit this down somewhat. We'll see. Let me just read through the rest of the essay assignment. So, essay assignment for Chapter 2, Dynamics. So, in this essay assignment, you will see a couple unusual situations dealing with the forces, which will help highlight common intuitive mistakes students make in applying Newton's laws. Please watch the following 2 videos and answer some of the questions below. Alright, so I'll go through the videos relatively quickly. So for zero-G flight, again, I don't think I covered this in any of the lecture video material. So let me turn the captions on and I'll just skip around. It's like 3-minute video. If you want to watch the whole thing, you can go to the BBC channel, search for zero-G flight, wonders of the universe, falling. There's also a video code here if you want to type that thing. So it's showing what's called a vomit comet sometimes. It's an airplane that flies in parabolic arcs, and in the kind of the downward parabolic arc, it'll simulate the microgravity situations that astronauts experience in orbit. So that's what the purpose of this vomit comet is. It helps people kind of get used to the zero-G kind of feeling, and the video shows people floating around as the airplane does that maneuver. I think each kind of period of microgravity lasts for maybe 15 seconds, not long. So you have to kind of stitch these together. So kind of different from being in a space station where you are under microgravity for much longer. So okay, that's the first video, and the second one, it's actual astronauts who are at International Space Station, and they're doing a demo for I guess it's made by NASA station astronauts to do experiment for Cosmos. I guess that's one of the shows by Neil deGrasse Tyson. I think that's the this astrophysicist's name. And it's pretty short, I guess. Again, for copyright reasons, let me not play the whole thing. And the main demo that they're doing is they're demonstrating Newton's third law. They are illustrating the action-reaction force. Now with this very light shuttle, you won't quite see the reaction force. So they add the other astronaut so that the two people have roughly the same mass. And you can see the person who pushed the other commander kind of gets pushed backward. And again, you can watch the video yourself. There's enough detail here for you to find it. So with all that, here are the questions. Let me just read each one in order, I guess. The questions 1, 2, 3, 4, and then I'll read the model answer. Yeah, let's hope this video is not gonna be too long. Okay, so question 1 here. Describe what you see in the zero-G flight video. What happens to the passengers as the airplane falls with the pull of gravity from Earth? Explain how the zero-G flight, which flies no higher than regular commercial jetliners, is different from regular airplane flights you may have been on and felt no sensation of weightlessness. And here's my model answer. Again, these are kind of open-ended. There are many other acceptable full credit answers. That's not exactly this. Describe what you see in the zero-G flight video. The passengers appear to float within the plane as the airplane falls with the pull of gravity, that is, as it goes into free fall. The zero-G flight is different from regular airplane flights, specifically in that it flies in parabolic arcs, designed so that in certain segments of the flight, the airplane is accelerating downward at g, 9.8 meter per second squared, like an object in free fall. Although the passengers are also accelerating downward, the passengers are also in free fall because both the airplane and the passengers are accelerating downward together. They don't appear to be falling relative to the airplane. But the gravity has not actually gone away as described below for question 2. Okay, let's just read the question and the model answer. In the zero-G flight video, the narrator describes, I think his name is Brian. I don't know who that is. Gravity is completely gone away. Is this statement true in the sense that there is no more gravitational pull by Earth on the passengers on the flight? If there's still gravitational pull by Earth on the passengers on the flight, why do the passengers feel weightless? What force do the passengers and we on the ground feel as apparent weight that these passengers no longer feel? As a side comment, the narrator says, I've cancelled gravity out. This is in reference to Einstein's equivalence principle, which we may touch on briefly in relativity, general relativity. For the moment, it is more instructive to think about this situation by considering only the real forces on the passengers. So my model answer for question 2, is it true gravity is completely gone away? No, not in the sense that the gravitational force is gone. Specifically, Earth's gravitational pull is still pulling the passengers and the airplane downward, which is why they are both accelerating downward at 9.8 meter per second squared. The passengers feel weightless because there are no more contact forces on them. There is no more normal force, also known as support force or apparent weight, on the passengers from the airplane, because the airplane is accelerating downward at the same rate as the passengers. It does not need to push the passengers up. Note some answers might draw an excellent comparison to skydiving, where the skydiver feels the air resistance, so they don't quite feel weightless. But here, as the air moves with the airplane, the passengers do not feel air resistance and experience a sensation closer to true weightlessness. But this comparison is not required for an answer to be considered correct. Again, open-ended. Question number 3. In the second video of astronauts doing a simple experiment, flight engineer Rick Mastracchio pushes expedition commander Koichi Wakata and the shuttle model he holds forward towards the camera, and he himself is seen moving backward away from the camera. Explain in one short paragraph how this is explained by Newton's third law. It helps to state what Newton's third law is. And let me read the model answer. Explain the astronaut's motions using Newton's third law. Newton's third law says that for every action, force, there is an equal and opposite reaction, force. But a clearer, if longer, statement is this. For every force object/person A applies on object/person B, action force, B applies an equal magnitude of force on A in opposite direction, reaction force. In the video, FE, flight engineer Mastracchio, pushes EC, expedition commander, Wakata in the forward direction. So EC Wakata accelerates forward. So according to Newton's third law, even though he is completely passive, EC Wakata is pushing FE Mastracchio back in the backward direction. You might call this the reaction force. So FE Mastracchio accelerates in the backward direction. Newton's third law ensures that these two forces are equal in magnitude, and since they have roughly the same mass, their accelerations given by Newton's second law are also roughly same. Last question, question 4. For a space shuttle in the vacuum of space, explain how the shuttle would propel itself forward. What gets pushed backward so that the shuttle is pushed forward? Identify the action force and the reaction force in this interaction. And please be specific for both the action force and the reaction force. Which object is exerting the force and which object the force is being exerted on. Let's look at the model answer for question 4. Explain how the shuttle propels itself forward. A shuttle, or any rocket, propulsion works through Newton's third law. The shuttle's engine is designed in such a way, we'll skip over the details, so that when combustion happens in it, the reaction products, water vapor and other gases, are pushed backward. If we call this shuttle pushing its burnt fuel backward action force, then the reaction force is the force of the burnt fuel pushing the shuttle forward. It's this reaction force that pushes the shuttle forward, and as you can see, the shuttle carries with itself the object that it pushes backward, its own fuel. And it doesn't need to push on anything outside of itself, not the ground and not the atmosphere, both in the vacuum of space and in the atmosphere. I think there was an old New York Times article criticizing, I guess, a space program for whether the rocket needs to push on the atmosphere to for the propulsion to work. This is kind of a reference to that. Okay, so that's for chapter 2. And I guess let me break this up because the rest are for unit 2. So let me, do the dramatic reading of the essay assignment and the peer grading, which contains the model answer in a separate section of the video. Okay, so let's continue on to Unit 2 essay assignment, starting with the Chapter 3 essay assignment. And, it's shorter. Good. Here's the video. And this is a little bit harder to find the video just because there's a bit of a controversy about this particular MIT professor. But if you want to, again, for copyright reasons, I won't play the full video. I'll just skip around. It's a kind of pendulum-like demo. He first kind of demonstrates it, showing how it can shatter that glass. And you kind of have to watch carefully how it's starting the motion. And that'll swing back and, break the glass. And then now he's going to replace it and do the demo himself. And he does there's a very subtle difference here that you have to watch carefully. And he will release. And just to stay there. He's taking longer than I thought he would. He's joking. Yeah. All right, so that's the demo. And actually, if you look at it carefully, it actually doesn't, come anywhere close to his chin. There's like a centimeter or two of gap there. So that's the video. Again, if you want to find it, watch the whole thing yourself. I guess this one, I'm pretty sure the guy who's uploading it is also violating MIT's copyright, but fine. So, the questions. In the video, the professor risks his life in demonstrating conservation of energy by showing that the pendulum or wrecking ball will not crush his chin. How is it that just prior to his demonstration that did not crush his chin, the pendulum did shatter the window that was mounted on the frame that he removed? Please explain what the key difference must have been in order for the wrecking ball to shatter the window on its return journey. Again, let me bring up my model answer, and I will do the dramatic reading of the model answer. Number 1, how is it that the pendulum didn't shatter the window? The key difference here is whether the professor gives the ball an initial push, hence some initial kinetic energy, or not. When he wanted to smash the window, he gave the ball a little push and initial kinetic energy, meaning that the ball had enough energy to go higher than its initial height, smashing the window. When he did not want to smash his own chin, he took great care to release the ball from complete rest, as he took great pains to describe and dramatically enact. So with the zero initial kinetic energy, the ball does not have enough energy to go higher than its initial height, the position of maximum potential energy. Okay, question number 2. If you watch the video carefully, you will notice that the wrecking ball actually does not even touch the professor's chin. It comes within a few centimeters of touching it. Assuming the wrecking ball was indeed released from rest while touching the professor's chin, and his chin did not move back since there was no room for him to, can you explain why the wrecking ball did not return to its original height? What processes are responsible for this loss of mechanical energy? And my model answer, again, these are all kind of open-ended. There are other excellent answers that doesn't have to be identical to these. So the question, can you explain why the wrecking ball did not return to its original height? What we are looking for is friction and air resistance as the culprit that reduces the total mechanical energy of the pendulum. Whenever you see mechanical energy not conserved, chances are very often you can blame it on friction and air resistance, which is a form of friction. This is why we took some time to describe friction when we describe the forces. In physics, we often like to describe things in idealized setting where friction is zero, but when we make comparisons to real-world objects, we have to remember that there is almost always some friction around. It is very difficult to make it exactly zero. Here, the biggest thing is probably air resistance. At least when I simulate, once you get rid of air resistance, then pendulums become perpetual motion machine in simulation. Okay, let's look at the next chapter. We have essay assignments for chapter 4, impulse and momentum. I'm trying to go a little bit faster so that I don't have to cut out as much in editing. Okay, so one of the areas of science and engineering, good. Oh, I guess let me just read this out loud. So one of the areas in science and engineering where a good understanding of physical concepts of impulse, momentum, and Newton's third law is indispensable is rocket propulsion. Following 3 videos give some details of rocket propulsion from chemical rockets, which were used for Apollo moon missions, and I guess now Artemis moon missions. We are still using chemical rockets. And are continuing to be used for satellite launches, supply missions to the International Space Station, etc., to ion engines, which some hope will be the prime mover of future space exploration. Please watch these videos and answer below 2 questions. The third video is a bit long. You should be able to answer the questions without having watched the entirety of the last video. So again, I will load the video and I will just skip around, just showing some key parts. This how a rocket works video, you'll just have to watch the whole thing. I think it's short enough. Again, so you can find it at Sabin Civil Engineering channel. Look for how a rocket works video. There's also a video ID there if you want to use it. So yeah, I think this goes into quite a bit of technical detail, not all of which I'm super familiar with. So, and some of these details are not important at the level of the detail that we are covering. Really, the main thing we are looking for is conservation of momentum and action reaction force. So yeah, I think a lot of this, you should really go and watch it yourself. Does it give us the exhaust velocity? I guess it's not giving us the exhaust velocity. Yeah, so I think you'll get a lot more just watching it yourself if you are interested. So this is for the chemical rocket operation. And this, I believe, is an ion engine, the same as the third video. So I forget if I wrote any essay timed assessment question dealing with the ion engine. It's possible that I didn't. Is the subtitle on? I can't tell. This is only 2 minutes. So I think this is super short video. Just that's not an ion engine. That's chemical engine. And let me see if there's a later. I think that's yeah. They are demonstrating the kind of the research ion engine. Yeah. So that's sort of what it looks like. This is ions kind of I guess lighting up the air. I think. Don't know if ion engine drive plume will be visible in vacuum. Maybe not. I'm pretty sure this is not in vacuum. Yeah, so this is the shorter video. And the main advantage of an ion engine is that these are moving really fast. The particles you are ejecting, the reaction mass, is moving at a substantial fraction of speed of light. So you get more thrust out of less amount of mass. So this longer video will, I think, explain more of how does ion engine work. 9-minute video. And yeah, why so I think there are no working designs of ion engine that'll let you escape gravity. With the ion engine, it's more about how for the duration of the thrust that you can achieve, compared to chemical rockets, which have a pretty short burn time. So I think so that's the kind of the diagram of the ion engine and the electromagnetic setup that'll push it. So the key main thing is that it ejects particles at really fast speed. And I think there are people kind of looking at this for maybe attitude control, I think. I remember The Martian, the novel and the movie. They imagined the manned Mars mission that uses ion engine. Anyways, you can again, find the whole full video yourself at the channel, Fraser Kane, how do ion engines work, and it's still available. I didn't play the whole thing for, again, copyright reasons. So let's look at the questions. So there are 2 questions here. Let me just read the first question, and then again I will read my model answer in the peer grading assignment. In multi-stage chemical rockets, earlier stages, starting with a solid fuel rocket booster, are separated from the later stages and eventually the payload after the fuel is exhausted. In terms of Newton's laws, conservation of energy and/or ideas of impulse and momentum, explain how this multi-stage design is better than single-stage design, what might have been called single-stage to orbit design. I think this is a link to probably Wikipedia. So single-stage to orbit design, there's a whole article that you can read. The first video gives a little hint with reference to mass. Expand on that passing remark in your explanation. So let me bring up the model answer. And I guess it's the idea of dead weight, maybe. Let's see how I phrased it. I don't know, it's been a while since I've written these model answers, so I don't remember exactly what I wrote in there. I don't know if I mentioned the dead weight. So, question, how is the multi-stage design better? So, as the first video describes, at about 3 minutes and 15-second mark, each spent stages are abandoned in order to reduce weight and mass and make it possible to achieve greater acceleration. Now, here is a detailed explanation using A, Newton's laws, B, impulse and momentum, and C, conservation of energy. It is not necessary for a correct answer to use all these approaches, but a correct answer should include at least one approach in the detailed explanation. So this is like 3 times what would be full credit answer. A, Newton's laws. This is a simple application of Newton's second law. If each stage of rocket can produce a fixed amount of thrust, force, then the lighter you can make the mass of the rocket, the more acceleration you will get. And the more acceleration, the higher velocity and higher orbit you can achieve. Note here, it is important to distinguish mass from weight. It's the mass that matters directly. So in order to do that, I did use the word dead weight. The dead weight from earlier spent stages are discarded. so that these useless parts are not accelerated along with the payload that we want to put in orbit. B, impulse and momentum. Conservation of momentum holds in rocket propulsion. By pushing out rocket propellants in one direction with a great momentum, the remaining rocket is propelled in the other direction with an equal momentum, equal amount opposite direction, keeping net change in momentum 0. So, given the same amount of momentum, P equals mv, given to the remaining rocket, the less massive we can make the remaining rocket, the more velocity it would gain. So the dead weight from earlier spent stages are discarded. C, conservation of energy. The process of putting the rocket payload in orbit is essentially a process of putting in enough energy into this mass to have gravitational potential energy necessary to achieve the orbital height, along with the correct kinetic energy. It also needs velocity in the correct direction, etc. But we are ignoring that detail for now. Since the gravitational potential energy is proportional to mass, the smaller we can make the mass of the objects we push up to a particular height, less energy will be needed to place the eventual payload in the orbit. So as soon as parts of the rocket are not needed, that is earlier stages with the spent fuel, they are discarded so that the dead weight does not need to be dragged up to higher heights, which wastes energy. Unless, I guess, if you are worried about reusability of rockets, which is, I guess, more of a thing these days. Yeah, so that's all the 3 possible, each individually full credit answers for question 1. Let's look at question 2. I think it's going to be about ion engine. In the videos for ion engines, the 2 videos number 2 and 3, following statement, paraphrased, is made. Large velocity of ions being pushed outward generates a very efficient production of thrust, or propulsion. Explain, in terms of conservation of momentum, why that is. Also explain as necessary what efficiency here is referring to. And my model answer. And I don't think I really defined the efficiency in this context. So the model answer will define it, but different people might have different ideas of efficiency in this context. Why is large velocity needed for efficient production of thrust? The basic principle of rocket propulsion is the same across all propulsion methods that work in space. You throw a part of the rocket backward, and the reaction force pushes the remainder of the rocket forward. Newton's third law and conservation of momentum. Since there is a limited amount of rocket, except in some special designs where the rocket collects surrounding material, like in science fiction, you want to achieve the biggest bang for the buck. And here the bang, that is what you get, is the impulse you gain for the remainder of the rocket. And the buck, that is what you pay, is the amount of mass you have to throw, the reaction mass. From conservation of momentum, impulse gained for the rocket is equal in magnitude to the impulse carried away by the propellant. Impulse is equal to momentum of the propellant, which is the mass times the speed of the propellant, mass also of the propellant. And the greater the speed of the propellant, the less mass you need to eject in order to achieve the same thrust. This is the sense in which chemical rockets are inefficient. The propellant velocity isn't very high compared to speed of light, so mass ejected is very large. And ion engines are efficient. The propellant velocity can start to approach the speed of light, so for the same impulse gained, mass ejected is smaller. We will see this type of discussion of efficiency later in the course. You can say in general, efficiency is defined in this way. Efficiency is what you get divided by what you pay. And what you get and what you pay are dependent on the context. And we'll be talking about this in the context of thermodynamics. Okay, we got 2 more chapters remaining. Let's look at that. Chapters 5 and 6. So chapter 5 is the one that had that Chladni plate thing. Let's see, how many videos do I have? Oh, just the one. Okay, yeah, good. I think we're making good time. So I don't know if she's still actively making videos. She went through what's called a long COVID during the COVID pandemic. This is one of her older videos. But again, I encourage you to watch the full video. Go to the Physics Girl channel. Look for singing plates, standing waves on Chladni plates. By the way, I only recently learned how to pronounce the word Chladni. So in the past videos, I might have had said Chladni. I think it's pronounced Chladni. I guess it's a German name. So let me skip around. So she's demonstrating. Yeah, I think I've actually shown this pattern in the one of the newly recorded videos that I have. But yeah, these require higher frequencies that my demos didn't quite work out. And here now she gives a longer explanation of how this works, and that's where I recommend that you go to the full video and watch it. In the demo I have, I don't quite do the full explanation. I just have the illustration of the nodal lines, and yeah. So yeah, and somehow this video is still shorter than the lecture section in which I redo this demo. So I guess professional YouTubers. So question 1. Chladni plates are used to demonstrate a standing wave visually by sprinkling some particles, usually salt or sand, over a plate vibrating at a resonance frequency. The particles are seen gathering at particular locations and vibrating away from other regions of the plate. What is the one key difference between the locations where you see particles gathering and regions where you see them moving away from? And let me bring up my model answer. And let's look at that. So here's the answer to question 1. What is the one key difference between the locations where you see particles gathering and regions where you see them moving away from? The key difference is amount of vibration over time. On Chladni plates, particles bounce away from the vibrating parts of the plate and collect in the parts of the plate that are not vibrating. So the pattern of sand seen on the two-dimensional plate illustrates the nodes or nodal lines of the standing wave pattern for the resonance frequency. Somewhere in the empty region are antinodes, defined as the point where the amplitude of vibration is at a maximum. Question 2. In your own words, describe important features of a standing wave, either two-dimensional in the case of Chladni plate or one-dimensional like wave on a string. What is standing in a standing wave? Hint, define and describe what nodes and antinodes are and how they form. So here's my model answer. Again, your own answer might be a little different. It's fine, it's open-ended. So what is a standing in a standing wave? A standing wave displays oscillations at a particular frequency. However, unlike periodic traveling waves that appear to move from one point in space to another at a particular speed, that is wave speed, a standing wave is standing, not quite the same as a stationary. What is standing in a standing wave is its pattern, the shape of vibration over time. This is most clearly illustrated by the fixed positions of nodes and actually antinodes too, because antinodes are where it's moving the most, but the position of antinode is not moving. Nodes are locations in a standing wave that never move. The wave medium is actually stationary, no oscillation over time. And antinodes are locations that move the maximum amount. The amplitude of oscillation is greater than at nearby points. It is these nodes and antinodes that are standing in a standing wave. And the overall pattern. This is just a phrase I like to say. Usually I say the nodes are the standing part of the standing wave. The nodes and antinodes are formed through wave interference. A standing wave is formed when two traveling waves of equal amplitude and equal frequency, so equal wavelength, overlap as they travel in opposite directions. They interfere in such a way that at certain locations you always get destructive interference. Displacement of one wave cancels out displacement of the other wave, which is where you get nodes. And at other locations you get constructive interference. Displacements of one wave and the other wave are in the same direction, so they add to each other, which is where you get antinodes. And here's a grading note. A correct answer does not need to go into this much detail. The important parts are the description of nodes and antinodes. Okay, I think we are almost at the end, the last chapter, chapter 6. And, you need to also cover chapter 7, but there's no essay assignment for fluid. So chapter 6, rotation. And I think I did include a Q&A about one of these videos, this video, and the questions in the one of the lecture sections. So you will see that. But let me just show you the videos. So this is MIT physics demo. I think I might not have to play this thing because I have my own the bicycle wheel gyroscope demo. So, but if you want to watch this video, it's at MIT Tech TV, MIT Physics Demo, bicycle wheel gyroscope, and I think by doing that he's making it spin, and and when he releases it from like this position here, that's where you now see the precession. It's kind of fun, really counterintuitive motion. So now in this demo, there's no real explanation other than as the wheel slows down, it kind of falls down into this position. You have that. Let's look at the Veritasium video. This is from 13 years ago. I feel like a Veritasium video these days are quite different. What? Why is it in Chinese? Okay. Oh, I guess there are no English is only auto generated. It's fine. So again, if you want to watch the full video, you can go to the Veritasium channel. It's still around. Look at gyroscopic precession or use the video ID here. And so he go through this brief explanation of vectors, and then I think he also describes how rotating things have a vector like properly, and that's the explanation that I don't really do in the lecture because that's really something we do in physics 4a. Oh, and I guess this is angular momentum. Now I see that the subtitle, I can tell it's angular momentum is talking about, not angular velocity. So, yeah, I think you really have to watch the video from beginning to the end to get the sense of it. Skipping around isn't quite as good. So these are the multimedia associated with these questions. Let me start out with the question 1. In your own words, please explain why the bicycle wheel does not swing downward when supported only at one end, if it is made to rotate around its axis before letting go of the other end. Please do use the terms used in the video, also in your textbook and my lecture, but phrase them in your own way rather than transcribing what was said in the video. Let me bring up the model answer. Explain why the bicycle wheel does not swing downward. And this is a note for the peer graders just saying, be generous. Because it is difficult to give a quick answer here that won't make immediate sense, I recommend you rewatch the second video as many times as you need to until you feel you understood it. Below are some concepts that are important for you to understand in understanding precession. A. Relationship between force and momentum. Force is rate of change of momentum, or to say it differently, force causes momentum to change. Force times the duration that the force is applied, that is impulse, is change of momentum. B. Relationship between torque and angular momentum. Torque is rate of change of angular momentum. That is torque times the duration of time you apply the torque. You could almost call it angular impulse, except no one does, is change of angular momentum. The best way to get an intuition for torque and angular momentum is by analogy to force and momentum, and the lecture does describe that. With A and B in mind, it is important to understand that as the wheel hangs vertically, with the handle being horizontal, there is a torque acting on it due to gravity. See the explainer video from Veritasium for picture. This torque will cause the wheel's angular momentum to change. And this change, magnitude and direction, is the same regardless of anything else that happens. So there's change in angular momentum from the torque due to gravitational force. All the difference between the two trials, one where the wheel is not spinning and one where the wheel spins, comes from the angular momentum of the wheel. One where it has initially zero angular momentum and one where it has initially non-zero angular momentum. When the wheel has zero angular momentum to start, the torque due to gravity causes angular momentum to increase in its direction. There are arrows, it's very counterintuitive direction. And all of this amounts to the swinging down motion you are used to seeing. But imagine describing it like a rotation about a horizontal axis. When the wheel has some angular momentum, the torque due to gravity is in a direction perpendicular to this angular momentum. See the explainer video for picture. The small change in angular momentum caused by torque due to gravity, still in the same direction as the above, causes the direction of total angular momentum to change, but not its magnitude. An analogous situation you can look at is a centripetal force that we covered in uniform circular motion. Centripetal force is perpendicular to existing momentum of the object, and the change in momentum due to the centripetal force causes the direction of the momentum to change, but not its magnitude, resulting in uniform circular motion over time. As the direction of total angular momentum changes, the wheel must be changing its orientation so that axis of its spin is still pointing in the direction of total angular momentum. And it's this change of orientation that we refer to as precession. Throughout the precession, torque due to gravity remains always in a direction perpendicular to the angular momentum of the wheel. So it is always changing the direction of the existing angular momentum, but not its magnitude. So that's question one. Kind of long because again it's a difficult question. And I think question two is the kind of short question I like asking to get a sense of if someone understands precession. Let me read the question first. The motion you saw in the video, slow horizontal rotation of a spinning bicycle wheel with its axis oriented horizontally, is called precession. And we can talk about rate of precession in terms of how quickly the bicycle wheel rotates horizontally. In the second video you saw, the bicycle wheel precesses once about every 5 seconds. Make a prediction and explain your prediction. If you spun up the bicycle wheel to spin faster before you let go of one end, will the bicycle wheel precess faster or slower? Or another way to answer the same question is, if you spun up the bicycle wheel to spin slower before you let go of one end, will the bicycle wheel precess slower or faster? And I think this is a good, sometimes harder question, because a lot of times people have the intuition to say, oh, you are spinning it slower, so it'll precess slower. And the correct answer is the opposite. Let me show you the model answer. So if you spun up the bicycle wheel faster before you let go of one end, will the bicycle wheel precess faster or slower? So with a faster spinning wheel, it should be precessing slower. This question is easier once you understand the answer in question one thoroughly. It comes down to one full precession involves a certain amount of total change, just in amount, not direction, of angular momentum. Because torque due to gravity is constant here, the rate at which angular momentum changes is constant. But when the wheel spins faster, its angular momentum is larger, so the amount of total change of angular momentum needed to bring it around the full circle is larger. Imagine angular momentum like an arrow, and the amount of total change of angular momentum needed like the circumference of the circle you get as you spin the arrow in one full circle with the tail at the center. So with a larger total change and the same rate of change, it'll take longer for the wheel to precess one full turn, meaning it'll precess slower if we started out spinning faster. That is, with a larger initial angular momentum. So that's the last question. And again, the purpose of kind of displaying these essay questions and reading out these answers is to help you with the essay timed assessment, where some of the questions were written with the assumption that you have seen and already thought through these questions, so that when you see them again in the timed assessment, it's a relatively quick thing to answer for anything that you understood the first time. So this covers everything. Thank you. Let me know of any questions.
Okay, so let me put have this on the side so that I can refer to different chapters and sections where we covered some of the things as I talk about it. So this is the setup, and what I want to talk about for next 20 minutes or so is recap of what you've been learning for the last 7 weeks, 6 weeks. So for the last 6 to 7 weeks, you've been learning really about mechanics, and it's quite a bit of a big topic, and that's why it's split into 2 units. We covered in the first unit in the kinematics and dynamics. We covered forces, and that's I think really center of mechanics. So when you call back to what we covered in the development of force concept, we try to introduce a force in an as simple way as possible, that it's a kind of push or pull. And and when we talk about mechanical description of universe, that's really what we are focused on. Mechanical description in the sense of um, connecting from cause to effect in a very simple way. So, so physics is the fundamental science, and one of the ways one of the ways we can do things in physics that sometimes difficult to do in biology or even in chemistry is that we choose to deal with the very simple systems so that we can go through everything step by step. So in this class we do less of that because sometimes going through those things step by step involves a lot of math. um, and as we are going through this operation of mechanical things, the key central idea that you will see everything connecting to are is force, the idea of force. Let me see, let me demonstrate what we mean by that. So we introduced the force in chapter 3, and if you call back to chapter 2, chapter 2 is where we covered the motion of we introduced the concepts like acceleration, velocity, speed, so that we can describe motion. And this force connects to motion through Newton's second law. Newton's second law says that net force is related to acceleration. So net force is mass times acceleration, or I guess in a way that that illustrates the causation a little bit better. Acceleration through which we can describe all motion. Once we know acceleration of something, then we can look at how its velocity changes. Once you know how velocity of something changes, then you can look at how its position changes. And you might remember from section 2.5 how we looked at some example of that. That if you have a constant acceleration, how from that you get all the other motion equations. So, so having that causation, chain of causation in mind, acceleration is determined by net force. It's a net force divided by mass. So, so force connects to all the things that you've seen in motion. Once you know, I guess in some kind of simplified sense, while highlighting the danger of oversimplifying, because sometimes the systems can get very complicated. So in some simplified sense, once you know force on an object at all times, then you might even say then you have determined motion of that object completely, or you can predict its future indefinitely into the far future. Um, for those of you who might be familiar with, who might have some philosophical training, you might have heard of something called determinism. And really, one of the inspiration for determinism is Newtonian mechanics, where once, ideally, theoretically, once you know all the forces acting on all the particles and objects, then the future of the system is determined. Now, all of this is quite oversimplified, so I don't want to give you an impression that this is what we believe in today. But force is important in the way that it gives us a handle on how to describe our mechanical universe. And now moving forward to Unit 2 content instead of Unit 1 content, this force is also basis of several other concepts that we've introduced. So um, the topics that you've been looking at past a few weeks and that you will be doing timed assessment on next week, we introduced energy and we introduced momentum. These are two twin pillars of classical physics, or, well, these are two most important quantities in physics. These are the, two of the most important conserved quantities. And in describing energy, how we connect to energy is that change of energy is related to work. When you do work, you change energy. And the way we define the work, which hopefully you have seen since our opening discussion in Unit 2, that we have this odd definition of work in physics that somehow seems to work out, that work done is a force times a displacement. Uh, Let me say delta x. So force somehow connects to energy, or at least the change in energy. And if you look back through chapter 4, you see that in each of these, with each of these forms of energy, how they were derived, how we analyzed it, they all connected to work. So they all, in some sense, connected to an idea of a force, how force affects energy. When we derive the kinetic energy, what we looked at was net force, how net force causes acceleration, and how the acceleration changes speed. And we could associate kind of quantity of motion that we can quantify through the work done by the force that was causing that acceleration. That's how we introduced the kinetic energy. And how we introduce the potential energy, both the gravitational and spring potential energy, it was through the idea of conservative forces. That when, with a certain kinds of forces, when these conservative forces do negative work, so they take out kinetic energy, that energy isn't gone. That these conservative forces are somehow predictive enough that when they do negative work and take out kinetic energy, you can kind of predict that you can bring it back. You saw that example with the gravitational potential energy. When I lift up an object, gravity does negative work. So as I push this up, it doesn't accelerate up as much. It doesn't gain much kinetic energy, but you can see that stored energy because when I let go of it, then it accelerates downward and all the kinetic energy comes back. And similar with the spring potential energy. So when we were talking about energy and change in energy, they're connected to force. And when we were talking about momentum, that also connected to force. I guess with the momentum, we do define the quantity of momentum that's in contrast to the quantity of energy. I think if you look at the chapter carefully, we never really define energy. Because so I think in chemistry maybe, or I think in sometimes energy is defined as ability to do work or something like that, but that kind of ends up being circular. So my own preference is to just not define energy, but leave it as a kind of quantity that we define so that, or whose like formulas for gravitational potential energy and spring potential energy and other kinds of energy later on, the quantity that we define so that it is conserved. So so we don't really give a very concrete definition of energy. In contrast to that, we do give a concrete definition of momentum. Momentum, it's a vector quantity. It's a quantity that has a direction, and it's equal to mass times velocity. That's momentum. It's quite simple. There's nothing more to say about that. And this quantity momentum also relates to force because, as you might remember from the chapter, we talk about impulse. And impulse is connected to momentum through impulse gives you the change of momentum. And in terms of defining what impulse is, we defined it as force times the duration of time. And there's quite a bit of similarity between how we define impulse and how we define work. Work was a force times the displacement. Impulse is it's also something related to force, and it's a force times the duration of time. And that small difference does have quite a bit of impact in terms of work. Both the force and displacement are vector quantities. And when you multiply them, you have to multiply it in a special way so that the end result doesn't have a direction. Energy is a scalar. Um, with the impulse, it's a force times duration of time, and duration of time is not a vector. It's just I guess you could call it a scalar. It doesn't have a direction unless not in space. So impulse is just a force vector times some scalar, and impulse, like momentum, is something that has a sense of direction. And so I guess I'm just highlighting both the similarity between impulse and work and difference between them. And what I want to highlight again is how all of this ties back to force. That it's the the study. So far, what we've been doing is study of force. Oh, and the discussion of momentum has it has important connection with something that we covered earlier. Earlier, when we were covering force, we had Newton's third law, which, to summarize, it says if an object, so there's a force, if there's a force on object B by A, then there's also going to be force on object A, which was before exerting the force, by B, and these two forces are related in such a way their magnitudes are the same and their direction is opposite. So we covered Newton's third law when we were covering force before, and it gets brought back when we do momentum. Newton's third law connects directly to momentum conservation. You saw that in action somewhere here. Let's see. The conservation of momentum. We looked at how the impulse due to action force and reaction force within a system, they cancel out and give you no net change in momentum. Okay, I see a question in the chat. Is time considered a vector in more advanced physics that cover space-time? That is a very good question that relates to, so the advanced physics that cover space-time is what we will get to in Unit 4 under special relativity. And I think one kind of, because we don't have quite enough time, we don't go into this depth about what we call four-vector formalism. So it's a way to handle space-time as one integrated geometry. Now, in that context, time is a component of the four-vector. So just like when you have when you have a vector in three-dimensional space, you can talk about its direction along one of the axes. Time becomes one of those axes. So in the more advanced physics that covers space-time, so we still wouldn't call time a vector on its own, but it would be one of the components of the four vector. So positive time, negative time, that sense of direction still does have meaning. And, it has meaning now too, future is different from past. Um, yeah, so that's one of the things that I hope you will see at the end of the semester that I'll talk about a little bit more. Um, yeah, and this kind of strange similarity and um, uh, similarity and difference between energy and momentum, they are also connected in a more intimate way in special relativity. For now, I guess I'm okay with just leaving it how they are connected both through force. And so that covers about half of mechanics too, work and energy and impulse and momentum. And the rest are what I might call application of mechanics. Oscillations and waves are probably some of the more interesting applications. And when you look at the oscillations, you can kind of see what kind of role force plays there. So let me see how good enough. So, so we started covering oscillations by talking about simple harmonic motion. And what drives simple harmonic motion is something like this. It's a simple harmonic is driven by a setup situation where you have a restoring force, like a spring force. When you pull a mass one way, then the spring pulls back. When you move the mass the other way, spring pushes back the other way. And in fact, there's a Hooke's law relationship. How much force there is, that's proportional to how much you displace it. And all of this, when you actually go through the math, it's very important in determining the properties of oscillation. We talked about things like natural frequency of oscillation or period of simple harmonic oscillator. And so, here you just see the formula. And in the process of deriving the formula, those relationship of the mass, relationship of the force on the mass and the displacement is very important. Um, so so oscillation is one of the applications of these mechanical ideas you have seen. And in fact, when we talk about oscillation, you see energy featuring it rather prominently. We talk about how in this oscillation, mechanical energy is conserved. And as this oscillates back and forth, goes from where it has zero velocity, but very large spring potential energy, to where it has zero spring potential energy, but very large kinetic energy. That potential energy is changing to kinetic energy and back and forth. So energy plays a role in describing oscillation. And things get more, if you recall, things get more abstract when we get to waves. So I think the direct connection is a little bit gets harder to see when we start talking about waves. And there is a reason for that. Waves are somewhat more general phenomenon than what we've been talking about in terms of energy and momentum. When we have wave, you can actually even talk about waves of people, like a stadium. I guess not these days, but more than a year ago, if you imagine going to a sporting event like a basketball game or baseball game or football game, sometimes you see these waves of people at the stadium, and you can actually describe waves like that in a mechanical way. Now, it's not quite a physics that describes the wave, it's more of a psychology. How long do you wait after you see someone next to you raising their hand, and that kind of determines how fast the wave propagates. So because waves are more general phenomenon in the world than simply energy and momentum, it's necessarily more abstract. But even so, you can see some connection of waves to how waves connected to other mechanical ideas. For example, um, think we say somewhere, so these are just defining terms. Um, okay, there's one mention of energy there. So, characteristics common to all waves, such as amplitude, period, frequency, and energy. And one thing that, um, yeah, talk so I don't bring it explicitly. So one of the things that waves do, that almost to all waves do, that waves that are people waves at the stadium don't, is it transports energy. And I think you can see that most clearly with the example of wave on a string. When you shake one end of the string, that as the disturbance propagates through the string, it's transporting the kinetic energy from one end of the string to the other end. So oscillations and waves, that's one of the examples of application of mechanics. And in the case of oscillation, you can see the direct connection to forces a little bit more clearly. And even in the case of waves, where it gets more abstract, in fact, when we talk about wave interference, you barely see any mention of energy or momentum or force, but there is some connection. And it gets a little bit farther away with the sound waves and those things. Um, and as we're wrapping up this recap of mechanics, I will say this. I want you to notice how many of the things that we talked about in mechanics before get brought back in rotation, except with a slight tweak. So before, we talked about acceleration as in a way of describing motion. We talk about angular acceleration. And before we talked about how force causes acceleration. And here in dynamics of rotational motion, rotational inertia, we talk about how something that's analogous to force causes angular acceleration. We call that torque. And I guess that word analogy is, I think that's the key to understanding rotational things. So many things in rotation, there's an analogy to things that we cover in linear motion. And that analogy, at least for me, it really helped me get a handle on a lot of things. I think kinetic energy is relatively simple, and that connects to like other, rotational kinetic energy is relatively simple. That connects to the linear kinetic energy, um, and the angular momentum and its analogous relationship to momentum, and how momentum relates to force, and how angular momentum relates to torque. Uh, that analogy is what helped me understand really angular momentum, especially when you look at really fun confounding effect like a gyroscopic effect. That's the topic of one of the essays that you will complete this week. So the rotation, it's a kind of a way to look at all these mechanical ideas all over again, but with a slight twist. No pun intended. From a slightly different viewpoint, because there's a lot of analogies that you can draw, um, and I hope that a different angle at which to, again, no pun intended. I need to find a better dictionary thesaurus. um, on a, just looking at these mechanical ideas that you've looked at before, in the case of linear motion, looking at it from a different viewpoint in rotation, I hope it'll help you better understand what you understood better, and maybe even highlight some of the things that maybe you thought you understand but didn't quite fully. And fluids, so we could have actually not done any fluid stuff, but I have to, so that we can say that we covered the Bernoulli's equation. And actually, a Bernoulli's equation does have a connection to what we've been covering. So, we covered the energy mechanics, and it's one of the important ideas. And what we call Bernoulli's equation, or Bernoulli's principle, which looks like this formula here, where it really comes from is the idea of conservation of energy. Each of these terms, they stand for, this term stands for kinetic energy, this term stands for gravitational potential energy, and the pressure is in some a little bit more disconnected way connected to amount of work that is done on the fluid. So yeah, I think I explicitly say here that all these are connected to the idea of conservation of energy. So fluids are another way we can apply mechanics, but the mathematics of it gets more complicated. That's why I would just cover it briefly and then move on. So it is a way to look at things, and I would, speaking as a physicist and someone who believes in the mechanical universe, mechanical description of universe isn't necessarily everything. We don't have a rational explanation of consciousness, and I I would have enough humility to say physics isn't everything, but it gives a very particular way to look at the world that I think allows a deeper understanding than pure philosophical view might. And all of that ties into, again, force, push or pull. Our goal here is to describe things as simply as possible, or when we can't, try to come up with a situation that's simple enough that we can try to describe it simply and understand it simply. So that's the overview recap of mechanics. Again, not quite exam review, because if we were on exam review, I didn't write down nearly enough for formulas, but kind of situating where we are, what's the point of all these chapters that we've been covering, how they connect together. With that, not seeing any questions, let me get started with that preview. So there is an organizing principle between units 3 and 4. You can kind of see it in the title. One says classical physics, the other says modern physics. And that's the organizing principle between units 3 and 4. There is a dividing line between classical physics and modern physics, one of which is the time. The development of modern physics took place around the turn of the 20th century, the beginning of 20th century. So modern physics is about 100, 120 years old. And that was a time of a lot of new development, a lot of perplexing phenomena, and all which resulted in development of quantum mechanics and special relativity. And the developments that took place then really changed the way people think about physics. It really changed the philosophy of physics. So we use that as the dividing line. The time before then is classical physics. The time after that is modern physics. And the things that we knew in classical physics, they still have influence, and sometimes there are many situations are well described by classical physics. I think your chapter 1 covered that. Um, and those are quite common everyday situations, so we continue to learn classical physics. And what a lot of modern physics amounts to is a modification of things we know in classical physics. So like electricity and magnetism, that's still very important, and that's why we still teach it and learn it. But I guess one philosophical difference that I would highlight is when I was talking about mechanics, I mentioned the philosophy of determinism, that the idea that if you have a system of stuff and you know enough about the system, you have complete knowledge of all the forces that will be acting on things, then how you might be able to predict the state of the system into indefinite future. And so the future is already determined. That's the determinism. And that's the kind of philosophy that would have been supported by things that we see in classical physics, in maybe not quite so much in thermodynamics, but definitely electricity and magnetism, study of gravity. um, they nothing in the theory, um, nothing in the theory confronts the idea presumption that you can have complete knowledge about a system and using that complete knowledge predict the future with no uncertainty. And and that's one of the things that we had to give up when we learned modern physics. In fact, in quantum mechanics, one of the things that we'll talk about is the uncertainty principle. How certain amount of uncertainty, certain, I need better thesaurus, that parts of some kinds of uncertainty is built into nature. That such a thing as complete knowledge about system is, it's a theoretically impossible. So 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 that's the beginning of modern physics, recognizing our limitations. I think you see quite a few philosophically minded people discuss quantum mechanics and its impact on philosophy, and there's some reason for that, because the physics before quantum mechanics was a completely deterministic physics, as in, in theory, you could do away with all the uncertainties and errors. The physics with quantum mechanics is a probabilistic theory. The theory predicts a probability of something happening, and there are many situations where, um, probability of a particular event happening isn't 100%. It's a 90%. It's a 50%. So there's a 50%, 10% chance of the other thing happening, and all that the best theory in the world can give you is the prediction of the probability, not certainty of which outcome will happen. So with that quick-ish description of the divide between classical and modern physics, this is what we do cover in classical physics. There are some more that we could cover, but this is where um, these are the topics that I thought were important for us to cover. Oh, I see a question. Let's see. Oh, it's why lots of people get into quantum computing confused when they don't get a hard result for their set of outcome probabilities. Yeah, and the ideas in quantum computing are, it's quite distinct from classical computing. And it's a yeah, I'll just leave that there, because there are certain algorithms that will run on a quantum computer that you simply cannot run on a classical computer, because we do those quantum states. I don't know if I'm doing this description justice. Sometimes you can run parallel computation, almost infinite number of parallel computations that would take infinite number of processes in a classical computer. But if you arrange the qubits right, then you can run such an algorithm on a quantum computer. It's a yeah. I have other things to say about quantum computer, but I'll leave that elsewhere. Classical physics. So we are really covering two main things here, or we're covering one thing, which is thermal physics, which is, I think, a practical in practical terms. This is probably the most important thing that we cover in this class, because thermal physics, they relate to heat engines, and heat engines they are they probably have more influence in modern life than anything else, because heat engines are what generates our electricity. Well, most of our electricity. A lot of renewables don't use the heat engines, but we are still using a lot of fossil fuel, even nuclear reactors. At some point in their power generation, they use a heat engine. What heat engines do is that they use flow of heat from hot to cold in contraption to divert some of the flow of energy into mechanical work. And that mechanical work can do useful things. So so what we study in, or what we describe in thermodynamics or thermal physics, is how all of that works, and how these heat engines have very limited efficiency. So so we cover thermal physics, and as you see, even in the topic headings, energy plays a very important role in study of thermal physics. So it introduces a form of energy that we haven't quite dealt with in mechanics, thermal energy, that can be described through temperature of a system and all that stuff, and and um, and we talk about how you can generate mechanical work that we've been talking about in mechanics from flow of heat. So that's one. And the remainder of classical physics, we are quite focused on the theory of electromagnetism. Now, it looks like it's divided into 3 chapters. And, to a great deal of extent, how we cover it in this class, it'll look like 3 separate things. In chapter 10, we cover electricity, electric charge, like a static electricity, how electric charges interact. Um, and in chapter 11, we talk about magnetism, permanent magnets, and all the stuff you can do with the permanent magnet, and maybe magnetic field lines that look similar to what you might have seen if you ever played with a bar magnet and iron filing. Now, what connects electricity and magnetism is, at the most fundamental level, what produces magnetic field is electrical current. And electrical current that we describe at the second half of chapter 10 with the conductors and the current through the conductors. So, so there's a connection between magnetism and electricity. And drawing all this connection, it does take quite a bit of math. So we kind of try to have our discussion around that so that we don't have to bring in calculus. But I will try to hint at that connection. The magnetic field produced by current, that's one. Magnetic force on a current carrying conductor is another one. Because this is where something feels a force from a magnet and there's nothing magnetic there. The only thing that's magnetic is current, electrical current. And the topic that properly marries these 2 topics, electricity and magnetism, is light. This is probably one of the greatest accomplishments in the 19th century physics. That the guy who gets credit is Maxwell. What's his first name? I forget his first name. James Clerk Maxwell. He he um, he developed a unified theory of electricity and magnetism. And in the process of developing that unified theory of electricity and magnetism, he predicted that you could have a wave of electricity and magnetism, or wave of an electric field and magnetic field. And and when he finished predicting it, he realized that the electromagnetic wave that he is predicting would move at this very fast speed. And by then, astronomers have measured the speed of light in orbital motion of things, and he predicted that he guessed that the electromagnetic wave that he was predicting, that it was light. And I don't think he saw his prediction confirmed before he died, but it was not long after it was confirmed. And so we lead the chapter on light with this section to highlight how light unifies our theory of electricity and magnetism. And this is quite a recurring theme in physics. You could almost say we are still living in the shadow of the development that was started with this unification of electricity and magnetism. If you ever heard of a grand unified theory, that's kind of where this comes from. Our physicists, the first taste in unification of our theories was with electricity and magnetism. So instead of two separate theories, one describing electricity, another describing magnetism, we have a single unified theory of electromagnetism. Now, having said that, the rest of the chapter, especially with the reflection, refraction, it doesn't really have much to do with electricity and magnetism. Because light is fun on its own, you know. If you ever played with a magnifying glass, you know what I'm talking about. Like, you didn't have to understand that it involved electric and magnetic field to have fun with the burning paper and stuff. So, um, so but we do cover light, and in some fundamental way, all these three chapters are connected. Um, and I think so. So as we get through Unit 3, I think by the end of week 11, I think week 11, week 12, um, through Unit 3, it'll what we cover will seem very rushed, that we don't spend a lot of time on any one single topic, and there's a reason for that. I really wanted to make sure that we had our last uh, quarter last 4 weeks of a semester available to cover modern physics. So I guess it'll still feel rushed, but given the choice of spending all 16 weeks through classical physics, physics that makes a lot of intuitive sense and is the basis of the philosophy of determinism, and ending things there with maybe a little bit of time to spare, and choice between that and one where it feels a little bit rushed, but where you have some amount of time to consider modern physics. I thought it would be better for you to have seen modern physics in this context of a physics class. Because a lot of things in quantum mechanics and special relativity, if you read about it in, popular science magazine or whatever, very often they mischaracterize certain things. And I want you to have a place where you can learn these things without any hype, just what they are, because just what they are itself is already very it does contain a lot of mystery, things that we don't fully understand. Uncertainty principle, we fully understand that. What we do struggle with is the wave particle duality. I guess it's not necessarily that mysterious these days, but the boundary between when these quantum mechanical effect, the wave nature of matter really matters, and when we can describe things classically, that's still something that's an area of active research. Um, so I think quantum mechanics is one thing that takes a lot of care to learn it and learn it properly. So we are heading there by week 12 or week 13. And special relativity is a lot of fun. I think just learning the relativity of simultaneity alone is I think if you are somehow able to fully grasp the simultaneity is relative, that alone will be an accomplishment for this conceptual class. Well, it will be an accomplishment for you. And the last bit of chapter 15, it covers some things. I think we have quite a few people taking this class because you are preparing for radiology and other other allied health fields. This chapter is why they are making you take this class, because we'll talk about radioactivity and biological effects of ionizing radiation. I'm sure in the radiology technician class, they will cover this themselves in a more proper technical detail, but I hope this chapter will be your if you haven't seen it already, that it'll be an adequate first introduction to these topics. So So we are getting there. We have the rest of the semester, but this is the 20-minute preview of what I can talk over for now. So that's everything I had, and that's probably all the time we have. Now, we unfortunately don't really get into quantum computing in this class, but yeah, I guess, yeah. Quantum computing, quantum information, that's its own thing. I remember when I was in graduate research, there were research groups in the physics department that was doing quantum information, and I have to tell you that the topics that they were doing research on looked very different from the kind of physics that I was doing, which was AMO physics, which dealt a lot with the quantum mechanics, but later. But there is some connection. I think some of the qubits are built using AMO physics stuff.